In this exercise, we're given a set, which are all the ordered pairs in R2. So this is the plane, right? And A has to be different from 0. That's the only requirement here. So the horizontal axis is excluded. Sorry, the vertical axis is excluded. And then in this set, we define this strange operation in which you have the two pairs and you multiply with this product that we define this way, and multiplication goes like this. So the first component is just obtain multiplying the first components of the two elements, and the second component is done with this weird operation, is this times this plus that. Okay, we need to prove that this is a non-abelian group. All right, well, this is clearly an operation that transforms elements of G into elements of G. Okay, there's no problem on that. So first thing we need to check is whether this is associative, right? So for that, we need to make the product of AB and CD, and then make the product with EF. All right. So the product of this is already written there. So it's like this: AD plus B, and then we have to multiply this by EF. All right. Now the result will be, well, the first component. The rule is that you have to multiply this first component, so it's ACE. And the rule here is that you have to multiply this component by this, right? So this by that, and add this one. So this by this and add this one. So I have ACF plus AD plus B. Okay, that would be the result of this. Right, let's do the operation in a different way. So let's multiply this by the product of CD and EF. So that would be AB multiplied by the product of this. The product of this is first component by first component, so CE, and then C times F plus D. So CF plus D, right? And now we have to repeat the operation. We have to multiply this by this. This is ACE, and this by that plus this. So ACF plus AD plus B. And now, as you can see, both are equal, so this operation is associative. So G1 is warranted, right? G1 is warranted. Now G2. G2 is, we have to find a neutral element here, right? So in other words, we need to find an element, CD, right? So that if you multiply AB by CD, what you get is AB again. But of course, if this has to be equal to this, AC must be A, and AD plus B must be equal to B. Okay, so from this equation, what we obtain is that C must be 1, right? And from this equation here, AD must be 0, so D must be 0. So now we have the neutral element. The neutral element is just 0, 1, 0. Okay, if you multiply anything by 1, 0, you will get the same thing, right, according to this. So there is a neutral element. The next one is to look for the inverse of any element, right? So what we need to find now is, again, given AB, we need to find something which multiply by this gives you the neutral. All right, but the multiplication of this is equal to AC AD plus B. So if this must be equal to 0, 1, then we have that AC must be 1 and that AD plus B must be 0. All right, so from this one we get C is equal to 1 over A. Remember, A is not 0. Okay, so this operation is correct. Okay, no, there's no problem. And from this one here, we have AD equal to negative B So D is equal to minus B divided by D. By A. Divided by A. So the inverse of AB is equal to 1 over A and minus B over A. So if you make the product of AB with this pair here, what you get is 1, 0. So every element has an inverse. You see, the only requirement for this to exist is that A is not 0, but A equal to 0 is excluded from the set, so that's okay, right? And finally, we have to check for commutativity and see that it doesn't hold. So you have here the product, and let's try to make the product in reverse. Okay, so that would be G4, commutativity, right? And first we need to multiply these two elements, so CA, right? And then we have to multiply this by this and add this one, so it's CB plus D. Okay, the first component is okay, coincides, but the second component is completely different, right? It's completely different. So it's not commutative. In general, it's not commutative. So this is a non-abelian group.